Welcome to the Deep Dive and our Science Corner series. If you're one of our intellectually curious amateur scientists, today we're diving into something pretty spectacular and sometimes scary, the science of volcanoes.
It's great to be here. Volcanoes really are a window into the Earth's core processes, a fascinating intersection of geology, chemistry, physics.
Absolutely. We've got a lot of ground to cover, looking at what they are, the hazards, the different types, what comes out of them, and even what's erupting right now. So let's jump right in.
Sounds good.
Okay, let's start with the fundamentals. Beyond just a mountain that might explode, what is a volcano, scientifically speaking?
Right. Well, at its most basic, it's an opening, a rupture in the Earth's crust. And through that opening, molten rock magma below ground, lava above, plus gases and other debris can escape.
An opening. But they don't just pop up anywhere, do they? There are specific places.
Precisely. The vast majority are found where the Earth's tectonic plates meet. These massive slabs of rock are constantly moving.
Right, the tectonic plates. So how does their movement actually cause a volcano?
Two main ways, primarily. Where plates pull apart or diverge. Think of the mid-Atlantic ridge. Magma from the mantle rises to fill the gap. It's creating new crust there.
Okay, like a seam splitting open.
Exactly. Then, where plates collide or converge, one plate usually slides under the other. That's called subduction.
Subduction, I've heard that term.
Yeah, and that process generates enormous heat and pressure. It melts the rock of the descending plate, creating magma, which then forces its way up. That's how you get volcanic chains like the Pacific Ring of Fire. It's famous for a reason.
Ring of fire, definitely. So pulling apart lets magma up, crashing together melts rock that comes up. What about where plates just slide past each other, like the San Andreas Fault?
Good question. Generally, you don't get major volcanism there. That sliding motion, the transform boundary, doesn't typically create the right conditions for large-scale melting needed for volcanoes.
Okay, that makes sense. But then, aren't there volcanoes not on plate edges? Like Hawaii, it's stuck right in the middle of a plate.
You're absolutely right, and that's where things get really interesting. It's called intraplate volcanism. Volcanism within a plate.
Intraplate, how does that work?
Two key mechanisms. Sometimes the crust within a plate gets stretched and thinned out. Think of the East African Rift, or even parts of the western U.S., like the Rio Grande Rift. This thinning can allow magma to push through.
So weak spots in the crust.
Sort of, yes. The other big one is mantle plumes, or hotspots. These are thought to be columns of unusually hot rock rising from deep within the Earth, maybe even the core mantle boundary.
Hot spots, like a blowtorch under the plate.
That's a pretty good analogy. The plate moves over this relatively fixed hotspot, and pop, 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 you get a chain of volcanoes. Hawaii's the classic example of that.
Fascinating. So different plumbing systems depending on the geology. Now, obviously, eruptions can be spectacular, but they're also dangerous. What are the main hazards we need to think about?
The hazards are significant, and they vary. First, the immediate obvious ones. Lava flows and debris flows, which are called the HARs. These aren't always slow-moving like you might picture.
Yeah. Not slow.
No, they can travel incredibly fast sometimes. Debris flows, especially, can reach speeds up to, well, 100 miles per hour in some cases. They just destroy everything in their path.
Wow, 100 miles per hour. That's devastating.
It is, but the danger often extends much, much further. Think about volcanic ash.
Right, the fine powdery stuff.
Exactly. Tiny pulverized rock and glass. It can be blasted high into the atmosphere and carried for hundreds, even thousands of miles.
And that's bad because...
Multiple reasons. It's a major health hazard if inhaled. It can contaminate water supplies. It's abrasive, so it damages machinery, buildings.
Yeah.
It reduces visibility to near zero sometimes.
And I remember hearing it's a huge problem for airplanes.
Oh, absolutely critical.
Yeah.
Jet engines operate at incredibly high temperatures. If they ingest that fine ash, it melts inside the engine and then solidifies on cooler parts like turbine blades.
So it basically clogs up the engine.
It can cause the engines to lose power or even fail completely. That's why airspace is shut down for hundreds of miles around significant eruptions. It's just too dangerous.
Makes sense. And these big eruptions, they can even affect the whole planet's climate, can't they? I've read about volcanic winters.
That's correct. Really large eruptions can inject huge amounts of ash and sulfur dioxide gas way up into the stratosphere.
Way above the weather.
Right. And up there, these particles, especially the sulfur dioxide converting to sulfate aerosols, act like tiny mirrors. They reflect sunlight back into space.
So it cools the surface down.
Yes, it leads to a cooling effect in the lower atmosphere, the troposphere where we live. At the same time, they can absorb heat radiating from Earth, causing the stratosphere itself to warm up a bit. But the surface cooling is the main effect linked to those historical volcanic winters, which sometimes led to crop failures and famine.
Incredible. A single event shaping global climate. Okay, let's shift gears a bit. We tend to picture volcanoes as, cone-shaped mountains. But they're not all the same, are they?
Not at all. Geologists classify them into four main types, based largely on their shape and how they erupt. You've got shield volcanoes, stratovolcanoes, cinder cones, and lava domes. Each has a distinct sort of personality.
Personalities, I like that. Let's start with shield volcanoes. The name sounds defensive.
Well, it actually refers to the shape. They're huge, but very broad with gentle slopes. Think of a warrior shield lying flat on the ground.
Ah, okay. Why so flat?
It's all about the lava. Shield volcanoes erupt very fluid, runny lava, low viscosity. Because it flows so easily, it travels long distances before cooling, building up those wide, gentle slopes layer by layer over many eruptions.
Low viscosity. Runny lava, what kind of rock does that make?
It's typically low in silica, maybe around 50%. This makes basalt, which is often rich in sodium, potassium, aluminum. The classic examples are the Hawaiian volcanoes like Mauna Loa and Kilauea, or the ones in the Galapagos.
Got it. Big, broad, runny lava. So next up, stratovolcanoes. That sounds more pointy.
They definitely are. They're also called composite volcanoes. Think of the classic picture postcard volcano-shaped steep slopes, often symmetrical cones,
Yeah.
like Mount Fuji or Mount St. Helens.
Composite, meaning made of different things.
Exactly. They're built up from alternating layers, or strata, of both lava flows and fragmental material ash, cinders, blocks from more explosive eruptions.
Ah, so they have explosive eruptions and lava flows.
Yes. Their lava is generally thicker, more viscous than shield volcano lava. It has intermediate silica content, maybe 60–64%.
Thicker lava. Does that mean it traps gas?
Precisely. Higher viscosity makes it harder for dissolved gases to escape peacefully. So pressure builds up and can lead to those much more explosive eruptions we associate with stratovolcanoes. The typical rock type is andesite. Think Krakatoa, Vesuvius. Historically significant and dangerous ones.
Right, the famous ones. Okay, third type, cinder cones. They sound smaller.
They generally are much smaller than shields or stratovolcanoes. They're basically steep, conical hills made almost entirely of tephra. That's the fragmented stuff, like cinders or ash ejected during mildly explosive eruptions. They often have a bowl-shaped crater at the top.
So just piles of volcanic debris.
Pretty much. What's interesting is you often find them on the flanks, the sides of larger volcanoes, or sometimes in clusters, almost like little parasitic cones.
Huh. Do they have lava flows too?
Often, yes. The eruption might start with that explosive fountaining of cinders driven by gas, but then finish with the quieter phase where lava oozes out from the base. The magma viscosity is usually intermediate to highish, making rocks like dacite or andesite. You see them in places like Lava Butte in Oregon or Mount Fox in Australia.
Okay. And the last one, lava domes.
Lava domes. These are often formed after an explosive eruption, sometimes right inside the crater of a larger stratovolcano. They're basically mounds of very, very thick, viscous lava.
Oh, thick, it can't really flow.
Exactly. It just slowly oozes out and piles up around the vent, creating this rough, dome-like or bulbous shape. Think toothpaste, but rock.
Rock toothpaste. What makes it so thick?
Extremely high silica content. We're talking 68–77% silica. This makes the lava incredibly viscous, resistant to flow. The rock type is typically rhyolite. Mount St. Helens has a famous lava dome that grew inside its crater after the 1980 eruption. The Mauna Inyo craters in California are another example.
Four types, four personalities, driven by lava viscosity. Let's dig into that a bit more. Viscosity, it's just resistance to flow, right?
That's the essence of it, yes.
Yeah.
Like you said earlier, think water versus honey or, well, cake batter. Lava viscosity is crucial. Low viscosity, like in Hawaii, lets gas escape easily, gives you those fluid flows, gentle shield shapes.
And high viscosity.
High viscosity traps gas. Pressure builds, leads to explosive eruptions and steeper-sided volcanoes like stratovolcanoes or those sticky lava domes. Even within a single flow, the cooler edges will be more viscous than the hotter inside.
Makes sense. And the gases themselves, what are they? And what role do they play besides getting trapped?
They're fundamental to why volcanoes erupt at all. The main gas is actually water vapor, H2O. Then carbon dioxide, KO, and sulfur dioxide, SO, are usually next most abundant. These gases are dissolved in the magma deep down under high pressure.
Like carrot dissolved in a soda bottle.
Perfect analogy. As magma rises, the pressure drops. The gases start to come out of solution, forming bubbles.
Like opening the soda.
Exactly.
Right.
These bubbles make the magma less dense, more buoyant, so it rises faster. If the bubble pressure gets high enough to overcome the strength of the rock above, boom, eruption. The amount of gas and the magma's viscosity determine how it erupts explosively or effusively.
So gas is the engine, viscosity is the control valve, kind of.
That's a great way to think about it. And silica content is the key factor controlling that viscosity valve. High silica, high viscosity, trapped gas, big boom potential. Low silica, low viscosity, gas escapes easily, lava flows.
You mentioned tephra earlier with cinder cones. That's the fragmental stuff.
Yes, tephra is the umbrella term for any fragment ejected during an eruption, whatever its size. If it's flying through the air, we might call it pyroclasts. If it forms a hot, ground-hugging avalanche of gas and debris, that's a pyroclastic flow, incredibly dangerous.
And tephra includes?
All sorts. Ash, that pulverized rock, mineral and glass, very fine. Lapilli, these are like pebble to gravel sized chunks, often solidified lava blobs, and volcanic blocks or bombs, larger chunks, blocks for solid rock ripped out, bombs or molten clots that shape in the air.
And this stuff has effects beyond just falling on the ground.
Oh, yes. We talked about ash in the stratosphere reflecting sunlight, causing cooling. It can also lead to acidic rain when gases like SO mix with water. It can stay up there for days, weeks, even longer after a huge eruption.
Wow. And what about specific rocks? You mentioned basalt, andesite, rhyolite. But what about things like obsidian or pumice? They seem quite different.
They are. And it mostly comes down to how fast the lava cools. Obsidian, that black, glassy rock, forms when very silica-rich lava, like rhyolite, cools extremely quickly, so fast that crystals don't have time to form.
Instant freezing, basically.
Almost, yeah. Pumice, on the other hand, is super lightweight, full of holes, right? It often floats.
Yeah, I've seen that.
That forms from gas-rich, usually high silica lava, rhyolite, dacite, andesite, during explosive eruptions. As the pressure drops suddenly, the dissolved gases expand rapidly, creating tons of bubbles. The frothy lava then cools very quickly, trapping those bubbles. That's why it's so light and porous.
So same basic lava, just cooled differently or with more gas?
In essence, yes. Rhyolite itself, when it cools slowly enough to form crystals but isn't full of gas bubbles, is just a solid, typically light-colored rock. Cooling rate and gas content make a huge difference.
Okay, that's fascinating. Now, given all this power and potential hazard, how do scientists actually keep tabs on volcanoes? How do they monitor them?
Monitoring is absolutely key, and it's a multifaceted effort. One of the mainstays is seismic monitoring, listening to the ground shake.
Earthquakes.
Yes, but not just standard earthquakes. Magma moving underground, gas pressure building, rocks cracking, all these create specific seismic signals. We use networks of seismographs to detect tiny earthquakes, swarms of quakes, and something called volcanic tremor.
Tremor, like a continuous vibration.
Exactly. It's often linked to magma flowing through conduits. By analyzing the types, locations, and depths of these signals, we can track magma movement and increasing unrest. Looking for changes is critical.
So, listening for trouble brewing. What else?
We also look for changes in the volcano shape, ground deformation. As magma pushes up from below, it can actually cause the ground surface to bulge or tilt, even if only by tiny amounts.
How do you measure that?
We use very precise techniques, things like GPS to track movement, tilt meters that measure tiny changes in slope, and even satellite radar INSAR, which can map ground level changes over wide areas very accurately. Swelling often means magma is accumulating near the surface.
Okay, listening and watching for swelling. Anything else?
Gas emissions are another big one. As magma gets closer to the surface, gases like sulfur dioxide, SO tend to escape more readily. We measure the amount and composition of gases being released from vents and fumaroles.
So sniffing the volcano's breath, basically.
Huh. You can put it that way. An increase in SO emission rates or changes in the ratios of different gases can be a strong indicator that fresh magma is rising and potentially nearing eruption. It's usually the combination of signals, increased seismicity, deformation, and gas changes that gives the strongest warning.
It sounds like a complex puzzle, putting all those pieces together. Speaking of activity, the source material gave a snapshot from late April 2025. What was the global picture like then?
Right. Well, as of late February 2025, there were 45 volcanoes globally considered in continuing eruption status. That's pretty typical. Usually it's somewhere between 40 and 50 ongoing eruptions worldwide, with maybe 20 or so actively erupting on any given day.
45. That's quite a few hotspots around the planet. Any specific examples from that late April timeframe?
Yeah, the report highlighted a few. Etna in Italy was showing strombolian activity. Those are like rhythmic bursts of lava and some lava overflow. Home Reef, a submarine volcano in Tonga, was producing ash plumes, and satellite data showed its underwater dome was growing, plus SO emissions.
Submarine volcanoes, too. Wow.
Oh, yes. Then Blusen in the Philippines had increased seismicity, followed by a phreatic or steam-driven eruption causing ashfall. The Zimiani in Kamchatka, Russia had a pretty significant uptick, tall ash plumes, hot avalanches.
That's intense.
And Poas in Costa Rica was having frequent small explosions from its crater lake, sending up ash and gas. Interestingly, analysis showed more juvenile material in the ash.
Juvenile, meaning new magma.
Exactly, indicating fresh magma from deeper down was involved, which could signal a shift in activity. So yeah, it really shows the constant dynamism. From gentle overflows to explosive ash plumes, it's always changing somewhere.
Truly underscores the need for that constant monitoring. Now, bringing it closer to home, where in the United States should we think about volcanoes being active?
Well, the states with the most active volcanoes are definitely Alaska, that's part of the Pacific Ring of Fire, a major subduction zone, and Hawaii, because of the hotspot. California and Oregon are next, mainly due to the Cascade Range, which is another subduction zone.
Alaska, Hawaii, California, Oregon. Makes sense.
But, as Ready.gov points out, it's not just those four. Other states and U.S. territories have active volcanoes too. We've mentioned Kilauea and Mount St. Helens. Alaska has many, like Great Sitkin, which was active recently. Even underwater, like a high seamount near the Mariana Islands.
It's quite widespread, really. What about a place like Utah? It's not the first state that springs to mind for volcanoes.
Good question. Utah doesn't have currently erupting volcanoes like Hawaii, but it has a really rich volcanic history, and you can see the evidence. Most are dormant or extinct now, but the features are there.
Like what?
Yeah.
The different types.
Yes. For example, Cedar Hill in Box Elder County is considered a shield volcano, though it last erupted over 1 million years ago. Mount Belknap in the Tushar Mountains is an older stratovolcano complex.
Okay.
And you can find cinder cones, too, like Diamond Cinder Cone down in Washington County, which is much younger, maybe 27,000 years old. Utah also has several volcanic fields areas with lots of past activity, like around St. George, Santa Clara Field, near Zion, Kolob Field, Markagunt Plateau. The Black Rock Desert Field has lava flows only about 660 years old.
660 years. That's geologically yesterday.
Pretty much.
Yeah.
Even the Bingham Canyon mine, famous for copper, is related to ancient igneous activity. And Bald Knoll is another young cinder cone. So, while not active today, Utah's landscape was definitely shaped by volcanism.
That's fascinating. It really puts geological time into perspective. Well, this has been an absolutely incredible journey into the world of volcanoes. As we wrap up, what are the main things you hope our listeners take away from this deep dive?
I think the key things are, first, the sheer diversity of volcanoes. They aren't all the same. Second, how they're intrinsically linked to the dynamic processes inside our Earth, like plate tectonics. And third, understanding these powerful forces through science and monitoring is absolutely vital, both for safety and for appreciating how our planet works and continues to evolve.
Right. So for all of you listening, remember that the ground beneath your feet isn't static. Earth is alive, dynamic, and volcanoes are maybe the most dramatic expression of that internal energy. Thank you so much for guiding us through this today.
My pleasure entirely.
And for you, our listeners, think about that immense power churning away inside our planet. Volcanoes are stark reminders of it. Maybe this discussion sparked your interest in a specific volcano or a type of eruption or the science of prediction. If so, definitely keep exploring. Until our next deep dive, keep asking questions and stay curious.